The success of the M2F1 encouraged NASA headquarters to approve development of heavyweight lifting bodies, which would be launched from the B-52 and powered by an XLR-11 rocket engine. Although the lightweight M2F1 could simulate the low lift-to-drag ratio, it could not simulate the high speeds that a heavyweight vehicle could achieve. The initial program involved building two different vehicles, the M2F2 proposed by NASA Ames Research Center and the HL-10 proposed by NASA Langley Research Center. The first flight of the M2F2 occurred on July 12, 1966, with NASA pilot Milt Thompson at the controls. From the start, it was apparent that the M2F2 had handling problems. Several times, the aircraft rolled back and forth violently as it descended. Each time, however, the pilot was able to regain control. Despite these problems, flights continued through the remainder of 1966 and into the new year. While the M2F2 was cautiously expanding its envelope, NASA pilot Bruce Peterson piloted the first flight of the HL-10 in December of 1966. Peterson discovered that the vehicle was barely flyable. Only by keeping the HL-10 speed up was he able to maintain control. This first flight, in the words of Langley engineers, once again demonstrated the value of flight tests as proof of concept. The vehicle was grounded, while engineers at NASA Langley and Dryden could come up with a fix. Although the HL-10 was grounded, the M2F2 program pressed on. Other pilots joined the program. In May of 1967, during the 17th flight of the M2F2, the handling problems came to a head during a violent crash. The M2F2 was significantly damaged and the pilot, Bruce Peterson, was seriously injured. Peterson eventually lost an eye to the accident, but otherwise recovered. This accident became the opening scene for the 1970s hit TV series, The $6 Million Man. Following the accident, the vehicle was rebuilt in-house by Dryden technicians and renamed the M2F3. The most significant change was the addition of a center fin, which greatly stabilized the aircraft at low speeds and solved the recurring problem of poor lateral control. Analysis of flight and wind tunnel data from the first HL-10 flight suggested flow separation on the outboard fins. After the leading edges of the outboard fins were modified, the HL-10 made its second glide flight in March of 1968, and now handled as well as an F-104. In February of 1970, Air Force pilot Peter Hogue took the HL-10 to a speed of Mach 1.86, the highest speed reached by any piloted lifting body. That same month, NASA pilot Bill Dana took the HL-10 to 90,030 feet, the highest of any heavyweight lifting body. Another lifting body, the X-24A, was sponsored by the Air Force and joined the flight test program. First flown in April of 1969 by Air Force pilot Gerald Gentry, the vehicle resembled a potato with 3 fins. Its shape would be later used in the design of the X-38 crew return vehicle. The final lifting body tested at Edwards was the X-24B. This aircraft was actually the original X-24A airframe, but with a sleek new outer shell grafted on. The once potato-shaped A vehicle now looked like a flat iron with a long nose and flat underside. This design gave the X-24B a much better lift-to-drag ratio. The initial glide flight was made in August of 1973 with NASA pilot John Mankey at the controls. The earlier lifting bodies and the X-15 had all landed on the lake bed, partially due to the lack of nose wheel steering, with which the X-24B was now equipped. In August of 1975, on its 27th flight, Mankey made a precise landing on the Edwards concrete runway, demonstrating the ability of an unpowered re-entry vehicle to make a pinpoint landing. Bill Dana made the final powered X-24B flight in September of 1975, which was the last manned rocket plane flight made at Dryden. In the 1960s, the U.S. had a supersonic transport SST program in competition with the British-French Concorde SST. Dryden contributed to that program through its supersonic flight research utilizing the XB-70 and the YF-12A. The XB-70 was originally conceived as a Mach 3 strategic bomber with an operational altitude of 70,000 feet. Only 2 experimental prototypes had been built by the time the Defense Department canceled the program. The large size of the XB-70 made it an ideal test bed for joint NASA-Air Force SST research. After a tragic accident destroyed the XB-72, the program proceeded with the less capable XB-71. Though limited to Mach 2.5, it yielded data on a number of issues facing SST designers, including aircraft noise, operational problems, control system design, sonic booms, high-altitude turbulence, and correlation of wind tunnel and flight data. In a similar fashion, the Lockheed YF-12A Blackbird's ability to sustain Mach 3 cruise speeds allowed NASA to expand its research capabilities and contribute to the SST program. The YF-12 Flight Research Program generated supersonic data on aerodynamics, propulsion, controls, structures, and subsystems. It also provided critical data in other areas such as upper atmosphere physics, noise tests and measurements, materials, and handling qualities. One particularly interesting experiment focused on heat transfer and exposed an insulated and chilled hollow cylinder instantly to Mach 3 flight conditions. YF-12 flight research data was complemented by a series of wind tunnel tests, laboratory experiments, and analyses. As a result, the combined ground and flight research generated vast amounts of information that was later incorporated into supersonic aircraft design. The first flight of the F-8 digital fly-by-wire aircraft in May of 1972 by NASA pilot Gary Creer ushered in a radical new flight control concept. Until the conception of the F-8 digital fly-by-wire vehicle, mechanical systems which ranged from steel control cables to hydraulics had been used to transmit a pilot's stick and rudder inputs to the control surfaces. Although some electronic fly-by-wire systems had been flight tested, these aircraft still retain the mechanical links as backup, the Lunar Landing Research Vehicle being the exception. By the late 1960s, digital computers had become more available and offered a lighter, more capable, and flexible fly-by-wire system. Dryden engineers proposed such a digital system be developed and flight tested. The computer initially used was from the Apollo 15 Command Module digital computer, but was later replaced with 3 AP-101 general-purpose digital computers. These were state-of-the-art computers in the mid-1970s. Each had 32K of memory, operated at 0.48 megahertz, weighed nearly 48 pounds, and cost $130,000. This system demonstrated fault tolerance by continuing normal operation after certain computer failures. The amazing contributions of the revolutionary F-8 digital fly-by-wire program were quick to follow. Today, fly-by-wire is used in almost every modern aircraft, including fighters, bombers, transports, and airliners. Another F-8 was also flying at Dryden during this time, the supercritical wing aircraft. The supercritical wing grew out of Richard Whitcomb's innovative research at the Langley Research Center. The wing featured a flattened top surface with a downward curve at the trailing edge. The flattened top reduced the tendency to generate shock waves, and the downward curve at the trailing edge restored the lift loss by flattening the top. The first flight of the F-8 supercritical wing was made in March of 1971 by NASA pilot Tom McMurtry. The flight test data confirmed wind tunnel results that the wing had lower drag than conventional wings at speeds just below Mach 1. The reduced high-speed drag offered increased cruise speed, improved fuel efficiency, and a longer range. In the decades since, supercritical wings have appeared not only on airliners, but fighters, heavy transports, and business jets. The third decade was a busy period with long-lasting results. The lifting body vehicles made great contributions to what would become the Space Shuttle. Both the digital fly-by-wire and supercritical wing research opened up a new era in aircraft design. Most modern aircraft in the sky today utilize some element of design that was pioneered at Dryden during this exciting period of flight research.